Hello everyone, my name is Basir Rafi, and this is the demonstration of the tool VeriODD. From YAML to SMT-LIB, automating verification of operational design domains. Operational design domains, ODDs, define the conditions under which an automated driving system ADS is allowed to operate. Current operational domains, CODs, reflect the actual driving situation at runtime. Ensuring that a COD instance lies within the ODD is a crucial step in safety assurance. Here we see an example of how ODD and COD are specified in YAML. The example is for a parking assistance system. The ODD consists of 3 modules. In the supported parking lot conditions module, we specify that the parking lot must be longer than 12 meters and that it must be a curve. These are the conditions where the system is designed to work. In the unsupported parking lot conditions module, we say that the system should not operate if the surface is covered with puddle or snow, or if the parking location is on the shoulder or partly blocking a lane. Finally, the parking lot conditions module is the overall module, and it combines both. It includes the supported parking lot conditions and, at the same time, excludes any of the unsupported ones. And to the right, we have a COD reflecting a real-time driving situation. We have parking lot length is equal to 13. Is curve is true. Surface is snow covered. Location is on shoulder. And now we would like to check if the COD satisfies the ODD. In practice, this means checking whether the conditions of the actual driving situation are admissible for the parking assistance system to engage. And to check that, we can use VeriODD. VeriODD has 2 modes, translation mode and verification mode. Let us have a quick look at the translation mode first. In the translation mode, I can choose between 2 inputs, ODD or COD. I would like to input my ODD here and translate it to propositional logic. This is for the use case that the user is not an expert with the ODD YAML syntax and they would like to review it on simple basis in propositional logic. And as we can see here for an example, the module supported parking lot conditions consists of parking lot length has to be greater than 12 and it has to be a curve which is equal to the module here in ODD, and by that the user can understand it on a very simple basis. ODD can be translated as well to SMT-LIB, and this is for the automated formal verification, which is already included in the verification mode. I can as well translate CODs to propositional logic and SMT-LIB. This is our COD, and this is it translated to SMT-LIB, and that's as well used for the verification mode, automated verification mode, and here it is in the propositional logic. And now let's go and check verification mode. And now I would like to check if my COD satisfies my ODD. So we input the ODD here, and then I will input the COD there. After that, to enable verification, I have to translate first. After I've translated, I would like to check my COD against the top level module, which is the parking lot conditions. So I'll have to choose the module from here, and then I will press on verify. The result is going to be unsatisfiable because, as we mentioned before, location on shoulder, surface snow covered, those both are unsupported conditions for the parking lot. But we can change them with supported conditions. For example, surface is dry and location is in parking spot. And now to enable verification again, I have to translate first, and then I will check it against the overall module, and then I will press on verify, and the result is going to be satisfiable. And because we have a satisfiable result, we can check get model. It returns one possible assignment to variables that make the asserted modules true. And we can exclude CODs, so we'll be able to check module consistency and if they have any contradictions. For example, I would like to choose the supported parking lot conditions and check for its consistency. It's satisfiable, it doesn't have any contradictions, but I can make it have a contradiction. For example, is curve is false and true, and in this case, this module will never become satisfiable. So I have to translate first, and then verify, and then it will be unsatisfiable. And I can as well have a look on the SMT-LIB syntax that is being sent to the solver or copy it. This was the demo. I hope you enjoyed it. Bye-bye.